So in this problem, we're given that the Sun is moving in a circular orbit about the center of the galaxy. The radius of its orbit is given by r of s, and the speed that the Sun is rotating at is given by v of s. We're also told that the Earth is moving in a near circular orbit about the Sun, with radius given by r of v, and period, which is given by t of v. Now in part A of the problem, we're asked to determine a formula for the total mass responsible for keeping the Sun in its orbit as a function of the Sun's mass m naught, as well as the four variables listed here. So let's start off by describing the motion of the Earth's orbit about the Sun. So by Newton's second law, we have that the net force on the Earth is going to be given by the force of gravity of the Sun on the Earth, which is big G times the mass of the Sun, m naught, times the mass of the Earth, which we'll call little m, divided by the radius of its orbit squared. Now that's going to be equal to the mass of the Earth times its acceleration, which is going to be the radial acceleration given by its circular orbit. So remember that the radial acceleration for circular motion is given by omega squared times the radius, where omega e is the angular velocity of the Earth above the Sun. So we know that omega is just 2 pi over the period. So we have that this is equal to m times 2 pi over the period t of e, all squared times r of e. So now, if we solve for g, big G times big M naught, we see that the m's cancel, so that big G times big M naught is going to be equal to 4 pi squared times the radius of the Earth cubed divided by the period of the Earth's orbit squared. So that follows from our equation above. Now if we analyze the motion of the Sun about the mass in the center of the galaxy, and by Newton's second law, we have that the net force on the Sun is going to be given by the force of gravity of this total mass on the Sun. So that's given by big G times big M, the total mass. That's responsible for keeping the Sun in its orbit, times the mass of the Sun, m naught, divided by the radius of the Sun's orbit squared. And that's going to be equal to the mass of the Sun, m naught, times its radial acceleration. So in this case, we're going to use a different expression for the radial acceleration. So recall that we can also describe the radial acceleration as the velocity of the orbit squared divided by the radius of the orbit. So now, if we solve for big G times big M, we see that the m naughts cancel, and we're left with the fact that big G times big M is equal to v of s squared times r of s. So now if we take the ratio of big G times big M over big G times big M naught, we get that m over m naught is going to be equal to v of s squared times r of s times t of e squared over 4 pi squared r of e cubed, which means that the total mass responsible for keeping the Sun in its orbit is v of s squared times r of s times t of e squared divided by 4 pi squared r of e cubed m naught. Let's make this more clear. So that's going to be capital M. So that's our final answer for part A of the problem. Now in part B of the problem, we're asked to evaluate the value for big M in terms of big M naught. So all we have to do is plug in our numbers for the different variables. So the velocity of the sun is given to be 220 kilometers per second. Square that times the radius of the sun, which is 30,000 light years. We also have to multiply by the period of the Earth, which is 1 year, and square that. We have to divide by 4 pi squared times the radius of the Earth, which is 1.5 times 10 to the 11 meters, and cube that. Now, I'm not going to work or show all the algebra and unit conversions involved, but if you do all the algebra correctly and make sure that the units match, we get that big M is going to be equal to 1.0 times 10 to the 11 m naught. So that's going to be our final answer, part B of the problem.